A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
I was scrolling through some of the developer subreddits this morning, and it feels like the rewrite in Rust meme has finally jumped the shark, but in the best way possible. It used to be this niche, slightly annoying suggestion people would throw at every project, but now, with the release of Claude Code and these more advanced agentic workflows, it is becoming a standardized industrial process. It is no longer just a joke on Twitter. It is a line item in engineering budgets.
It is a massive shift, Corn. Herman Poppleberry here, and I have been obsessed with this specific intersection of AI agents and systems programming for the last few months. Today's prompt from Daniel is right on the money. He is noticing that sane chatter developers using Claude Code to refactor entire code bases into Rust to squeeze out performance and efficiency. We are seeing a fundamental change in how we think about legacy code. In the past, a rewrite was a multi-year death march. Now, it is becoming a series of high-velocity AI sprints.
And Daniel's question is essentially, why now? We have known Rust was fast for a decade. We talked about the Linux kernel finally embracing it back in episode 1075, which was a huge turning point. But for the average developer who has not touched a line of Rust, what is the actual magic here? Why is it the target for all this AI refactoring? Why aren't we asking Claude to rewrite everything in Zig or Mojo, or just better C++?
The magic is that the Rust compiler is effectively a truth machine. This is a concept that has really gained traction in early 2026. When you use an AI agent like Claude Code to write Python or C++, the AI is essentially guessing based on patterns. It might produce code that looks correct and even runs 95% of the time, but it could have a hidden memory leak or a race condition that only shows up under heavy load. In Rust, the compiler is so strict about memory safety and thread safety that it rejects those hallucinations before they ever reach a production environment. It is the only language where the compiler is smart enough to tell the AI, I see what you are trying to do, but you are being reckless with memory, so I am not building this.
So, you are saying the compiler acts as a quality gate that is actually capable of disciplining the AI. If the AI hallucinates a non-existent API or a dangerous memory pattern, the compiler just says no, and gives a very specific error message that the AI can then use to self-correct. It reminds me of what we discussed in episode 1070 regarding the agentic secret gap. The idea that we need these automated guardrails to secure the AI developer workflow.
That is the core of why this is exploding in 2026. We are seeing a feedback loop where the AI writes code, the compiler identifies the logical flaws in memory management, and the AI iterates until the borrow checker is satisfied. It turns a high-risk manual migration into a high-confidence automated one. Anthropic actually ran this incredible experiment recently where they had 16 parallel Claude agents generating a full C compiler in Rust from scratch. It was something like 100,000 lines of code, and because they were targeting Rust, the agents could verify their own work against the compiler's rules. You just cannot do that with C++ because the C++ compiler will often let you do something incredibly stupid without a single warning.
I want to dig into that borrowed checker part, because that is usually the thing that scares people away from Rust. If I am a developer used to Python or Java, I'm used to a garbage collector just cleaning up after me. I do not have to think about who owns a piece of data. Why is getting rid of that garbage collector such a big deal for performance? Is it really worth the headache of learning these strict ownership rules?
Think of a garbage collector like a cleaning crew that has to come into a building, stop everyone from working for a few seconds, and sweep the floors. In high-performance applications, those stop the world pauses are killers. If you are building a real-time trading platform or a high-frequency network proxy, a 50 millisecond pause to clean up memory can be the difference between success and failure. Rust does not have a cleaning crew. Instead, it has very strict rules about who is responsible for taking out the trash as they leave the room. Every piece of data has exactly one owner. When that owner goes out of scope, the memory is freed instantly. No pauses, no overhead.
And those rules are enforced while the code is being written, not while it is running. That seems to be the key distinction.
Precisely. That is what we call zero-cost abstractions. You get the safety of a high-level language without the runtime penalty of a garbage collector. The code that the Rust compiler generates is often just as fast as hand-tuned C, but without the segmentation fault, nightmares that keep systems engineers up at night. This is why we see a 70% reduction in memory vulnerabilities when companies switch. It is not just that the code is faster, it is that it is fundamentally more robust.
You mentioned the Linux kernel earlier. We saw that move from experimental to permanent core part of the kernel at the summit in Tokyo late last year. Greg Crowe, Hartman actually said that the Rust drivers were proving to be safer and had fewer integration issues than the C drivers. But for someone not writing kernel drivers, where is the low-hanging fruit? If I have a massive Python monolith, I am not going to rewrite the whole thing in a weekend, even with Claude Code helping me. That sounds like a recipe for disaster.
You shouldn't rewrite the whole thing. That is a common mistake and a great way to burn out your team. The smart move is what people are calling the brownfield strategy. You identify your hot paths, the specific functions or modules that are doing 90% of the heavy lifting. Maybe it is a JSON parser, an image processing loop, or a complex calculation. You use tools like Pio3 or Maturin to write just that one piece in Rust and then call it from your Python code as if it were a native library. You keep the developer velocity of Python for the business logic, but you get the raw power of Rust for the performance critical parts.
We saw this with Polars, right? Everyone is moving away from Pandas for large datasets because Polars is backed by Rust. I saw a benchmark recently where Polars was performing 5 to 20 times faster than Pandas on the same data structures, and the user doesn't even need to know Rust to use it. They just use the Python API.
Polars is the perfect example of the Rust under the hood revolution. It uses Apache Arrow under the hood and leverages Rust's memory model to perform parallel processing without data races. When you use Python to orchestrate those Rust components, you get the developer speed of Python with the execution speed of a Ferrari. This is why the JetBrains State of Rust Ecosystem 2025 report showed such a surge in adoption. It is not just systems programmers anymore, it is data scientists and web developers who are tired of their Python scripts taking 3 hours to run.
I am curious about the AI side of this again. You mentioned the Anthropic experiment with the C compiler. What is it about Rust's syntax or structure that makes it easier for an AI to handle than C++? I would have thought the complexity of the borrow checker would make it harder for an AI to write.
It is actually the opposite. There is much less ambiguity in Rust. If you ask an AI to write a memory-safe C++ function, there are 5 different best practices depending on which version of the standard you are using. Do you use raw pointers, unique pointers, shared pointers? In Rust, there is the borrow checker. The AI does not have to wonder if it should use a raw pointer or a smart pointer. The compiler forces the correct choice. C++ has 40 years of legacy ways to do things wrong, whereas Rust has one modern way to do things right. This consistency is a huge advantage for large language models. They thrive on clear, enforceable rules.
That makes sense. It is like giving the AI a very strict set of blueprints instead of a vague sketch. This is why we are seeing companies like Microsoft prioritize Rust for things like direct write core. Mark Rusinovich has been very vocal about this. They are taking components that have historically been a source of security vulnerabilities, like font parsing and rendering, and systematically replacing them with Rust. Font parsing sounds like such a boring low-level thing, but it is actually a massive attack vector, because fonts are incredibly complex and often come from untrusted sources.
It is a huge security hole. If you can crash a font parser, you can often get remote code execution. By moving direct write core to Rust, Microsoft is effectively closing a door that has been open for decades. And it is not just apps. Microsoft open sourcing that Patina project, the UEFI boot firmware written in Rust that feels like a signal that we are moving past just apps and into the very foundation of how hardware boots up. We are talking about the code that runs before the operating system even loads. If that code is buggy, the whole system is compromised.
It is funny you mentioned Rusinovich. The guy's name is practically Rustinovich. He was born for this role. But seriously, the momentum is staggering. Even Android 16 is shipping with Rust in production for the anonymous shared memory subsystem, or ASHMEM. We are talking about millions of devices running Rust code at the lowest levels of the operating system. Google reported a 70% reduction in memory vulnerabilities in the parts of Android they migrated. That is a staggering number. If you told a security researcher 20 years ago that you could eliminate 70% of their bugs by switching languages, they would have laughed at you. They would have said it is impossible.
And yet, here we are. The data is undeniable. Rust reduces runtime memory errors by over 95% compared to C++. It is not just a marginal improvement, it is a generational leap. Let us talk about the specific applications Daniel mentioned, the prime targets. If I am a developer listening to this and I want to try out this Claude Code refactoring workflow, where should I point the AI first?
I would say start with your CLI tools. If you have any internal scripts written in Python or Ruby that take more than a second to run, those are perfect candidates. Look at the transition from grep to ripgrep. Ripgrep is often 10 to 100 times faster because it is built in Rust and uses sophisticated regex engines and parallel file walking. It is a massive quality of life improvement for developers. If you can turn a 30-second log analysis script into a 300-millisecond Rust binary, you've just given yourself hours of your life back over the course of a year.
What about network-heavy stuff? I remember Discord had that famous blog post about moving their read state service from Go to Rust. That was a huge moment for the community because Go is already considered a fast language.
That is another classic case. They were hitting these massive latency spikes in Go because of the garbage collector. Every time the GC kicked in, the service would stutter and users would see a lag in their message notifications. By moving to Rust, they did not just make it faster, they made the performance predictable. They eliminated those spikes entirely because there was no cleaning crew stopping the work. If you were building a proxy, a load balancer, or any kind of high-throughput messaging system, Rust is your best friend. Cloudflare has done the same thing with their edge network. They are moving more and more of their core infrastructure to Rust, because at their scale, even a 1% efficiency gain saves millions of dollars in power and hardware.
I want to push back a little on the speed aspect. People often say Rust is faster than C++, but isn't the reality more nuanced? In most benchmarks, they are neck and neck. I do not want people to think Rust has some magical go fast button that C++ lacks.
You are right to point that out. Rust is not inherently faster than C++ in terms of raw execution potential. Both languages compile down to very similar machine code. The difference is that Rust makes it easy to write safe, parallel code that is fast by default. In C++, you can write incredibly fast code, but it is like walking a tightrope over a pit of fire. One wrong move and you have a memory leak or a security hole. Most developers, when faced with that risk, write safer. C++ that is actually slower because they are being cautious. They add extra checks. They use slower but safer containers, or they avoid multi-threading because it is too hard to get right. Rust lets you be aggressive with performance because the compiler has your back.
It is fearless concurrency, as the marketing folks love to say. It sounds like a buzzword, but when you are trying to scale a service across 64 cores, being able to guarantee that two threads won't try to change the same piece of data at the same time is a game changer. It eliminates an entire class of bugs that are notoriously hard to debug. You know the ones. The bugs that only happen on a Tuesday when the moon is full and the server is at exactly 84% load. Rust kills those bugs at compile time.
We should probably mention the upcoming Debian requirement too. This is not just a corporate thing or a cloud thing. Debian has announced that by May 2026, their APT package manager will have hard requirements for Rust. That is a huge deal for the Linux ecosystem. It means that even the most conservative, stability-focused distributions are saying Rust is ready for prime time. If you want to contribute to the core of one of the world's most important operating systems, you're going to need to know Rust.
It is no longer a nice to have. If you are a systems programmer and you are not learning Rust, you are going to find yourself unable to contribute to core infrastructure in the next few years. The momentum is just too strong. And with AI agents lowering the barrier to entry, the old excuse that Rust is too hard to learn is evaporating. You can have Claude Code explain the borrow checker errors to you in real time as you code. It is like having a senior Rust engineer sitting next to you, pointing out exactly where you messed up your memory references.
I have actually tried that. I will paste a compiler error into Claude and ask, "Why is the borrow checker mad at me?" And it will give a very clear explanation of the ownership conflict. It will say something like, "You are trying to use this variable here, but you already gave ownership to that function over there." It is a much better way to learn than just banging your head against the documentation for 3 hours. It makes the learning curve feel like a staircase instead of a vertical cliff.
It changes the pedagogy of the language. Instead of reading a book for 3 weeks before you write a line of code, you can just start building and let the AI and the compiler guide you. It is a much more interactive, high bandwidth way to gain expertise. This is why we are seeing such a surge in the rewrite in Rust movement. It is not just that the language is better, it is that the tools for learning and implementing it have finally caught up.
So, we have got CLI tools, network proxies, and Python hotpaths. Is there anything else? What about WebAssembly? We haven't talked much about the browser side of things.
Rust is the undisputed king of WebAssembly right now. If you want to run high-performance code in the browser, think video editing, gaming, or heavy data visualization, Rust is the primary tool. Because it does not need a heavy runtime or a garbage collector, the compiled WASM modules are tiny and fast. It is opening up a whole new world of thick client applications that were previously impossible. We are seeing tools like Figma and Photoshop move more of their heavy lifting into Rust-based WASM modules, and the performance difference is night and day.
It feels like we are entering this era of AI automated systems programming. We spent the last 20 years moving to higher and higher level languages, Python, Ruby, JavaScript, because human time was more expensive than computer time. We were okay with inefficient code if it meant we could ship faster. But now, if the AI can handle the complexity of a low-level language like Rust, we can finally have our cake and eat it too. We get the developer productivity and the raw machine performance.
That is the most profound shift. We are reversing the trend of software is getting slower, faster than hardware is getting faster. For a long time, we just threw more RAM and more CPU at inefficient code. But we are hitting the limits of Moore's law, and efficiency actually matters again, especially for cloud costs and energy consumption. If you can cut your server bill by 60% by refactoring a few hot paths into Rust, that is a massive win for any business. In 2026, sustainability and cost efficiency are top priorities, and Rust is the most effective tool we have to achieve them.
I saw a report from Zenrose recently called, "Is Rust Still Surging in 2026?" and it confirmed this ongoing growth trajectory. It has been the most admired language in the Stack Overflow survey for 9 years straight now. People who use it really do seem to love it. Once they get past that initial learning curve, it provides a level of professional satisfaction that is hard to describe.
It gives you a sense of confidence that is hard to find in other languages. When your Rust program finally compiles, you have a very high degree of certainty that it is not going to crash in the middle of the night because of a null pointer. That peace of mind is worth the extra effort of satisfying the compiler. You can sleep better knowing that the truth machine has verified your logic.
I think for a lot of people, the aha moment comes when they realize they do not have to rewrite everything. I was talking to a friend who replaced a single Ruby script used for log processing with a Rust binary, and he went from waiting 20 minutes for a report to waiting 12 seconds. He did not even know Rust. He just used an AI agent to translate the logic, and then manually fixed a few borrow checker issues with the AI's help. He was stunned. He said it felt like he had discovered a superpower.
That is the rip-grep effect. Once you experience that kind of speed up, it is hard to go back. You start looking at every slow process in your workflow and wondering, could this be a Rust tool? And with Claude Code, the cost of finding out is almost zero. You can just ask the AI to take a crack at it and see what happens.
So, practical takeaways for the folks listening who are feeling the itch to join the Rewrite in Rust brigade. Number 1. Do not be a hero. Do not try to rewrite your whole stack. Identify those hot paths. Use a profiler to find out where your code is actually spending its time.
And use the AI as a partner, not a replacement. Let Claude Code or whatever tool you prefer generate the initial Rust code, but treat the compiler as your final authority. If the compiler is not happy, the code is not ready. Use those error messages as a learning tool. Do not just copy-paste. Try to understand why the compiler is complaining. That is how you actually become a better engineer.
And definitely look into Pio 3 if you're a Python shop. It is probably the most mature way to start sneaking Rust into a production environment without disrupting the rest of the team. You can keep your beautiful Python APIs and just swap out the slow engine under the hood. It is a very low-risk, high-reward strategy.
Also, check out the State of Rust Ecosystem 2025 report if you want to see where the industry is heading. It has some great benchmarks and case studies that can help you justify a migration to your manager. If you can show them that Google reduced vulnerabilities by 70%, they are going to listen.
Just tell them Mark Rusinovich said so. That usually works in most enterprise environments. He has been one of the most effective advocates for this shift, and his influence at Microsoft and Azure cannot be overstated. When the guy who wrote the sysinternals tools says we should stop using C++ for new projects, people tend to pay attention.
It does not hurt. And honestly, the security argument is often even stronger than the performance argument. If you can tell your CISO that you are eliminating memory safety vulnerabilities by design, they will be your biggest supporters. They are tired of patching zero-day vulnerabilities in legacy C++ code.
It is a rare win-win, where the developers get a more modern language, the operations team gets better performance and lower costs, and the security team gets to sleep better. It is rare that everyone is on the same side of a technical shift. Usually, there is more friction, but the benefits of Rust are so quantifiable that it is hard to argue with. When you see a 70% drop in vulnerabilities at the scale of Android, the debate is pretty much over.
I am looking forward to seeing what happens in May when Debian makes that switch. It is going to be a fascinating milestone for the ecosystem. I suspect we will see a lot more legacy. See tools getting the Rust treatment in the second half of this year as people realize they need to modernize to stay compatible with the major distributions. Dave Airley, the DRM maintainer, even said that his project is about a year away from requiring Rust and disallowing C for new drivers entirely. That is a massive shift for the graphics stack.
The momentum is definitely there. It is an exciting time to be a developer, even if it means we all have to learn how to play nice with the borrow checker. It feels like we are finally building a more solid foundation for the future of software.
Speak for yourself, Korn. I'll just keep poking fun at your enthusiasm while I let the AI do the heavy lifting.
Fair enough. As long as the code is fast and safe, I do not care who writes it. I think that is a good place to wrap this one up. We have covered the truth machine, the brownfield strategy, and why your next CLI tool should probably be a Rust binary.
It is a deep rabbit hole, but a very rewarding one. If you are curious, just start small. You do not need to be an expert to start seeing the benefits.
Thanks as always to our producer, Hilbert Fleming-Top, for keeping the gears turning behind the scenes. And a big thanks to Modal for providing the GPU credits that power this show. We literally could not do this without them.
If you are enjoying these deep dives, we would love it if you could leave us a review on Apple Podcasts or Spotify. It is the best way to help other curious minds find the show. We read every single one of them.
You can also find us at myweirdprompts.com for the full archive and all the ways to subscribe. We have over 1,000 episodes in the vault now, covering everything from the early days of LLMs to the latest in agentic workflows, so there is plenty to explore if you are new here.
This has been My Weird Prompts.
We will catch you in the next one.
Bye, everyone.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from slow